You ever code in Python and then switch over to C++ and just think, whoa, this is a completely different world? Or maybe you've wrestled with JavaScript and wondered why it does the weird things it does. Well, guess what? It's not random. Not at all. Every single programming language out there is the result of a bunch of really tough, really deliberate choices. Think of them like blueprints for thinking, ways to tell a computer what to do. So let's pull back the curtain and see exactly how these things are built, one big decision at a time. So, here's the million-dollar question, right? The one we've all asked ourselves during a late-night coding session. Why are some languages so easy to learn and write, while others are just screamingly fast? And more importantly, why can't we just have both? It feels like we always have to choose. And that tension, that big trade-off, well, that's pretty much the entire game when it comes to designing a language. Okay, so for the next few minutes, I want you to forget about being a student or a developer. You're an architect now, and you've got a job to do. You're going to design a brand new programming language right from scratch. You're going to face three massive choices. And these choices, they're going to define the very soul of your language. Everything from how a coder writes a simple for loop to how fast that code actually runs on the machine, it's all on you. All right, architect, let's get to work. Your first decision is a huge one. You got to ask yourself, who am I building this for? Is my language for people, making it super clear and easy to use? Or is it for the machine, designed for one thing and one thing only, raw, blistering speed? This all comes down to three big ideas: readability, writability, and reliability. First up, let's talk about readability. And this is simple, right? It's just how easy is it for someone else, or let's be honest, you, 6 months from now, to look at the code and actually get what's going on? You know, simpler is usually better. If your language has like 5 different ways to write a loop, a programmer has to know all 5. That's just more mental baggage. It's called multiplicity, and it can be a real killer for readability. And look at this, it's a perfect example. A tiny little choice that completely changes the feel of the code. So as the architect, what's your vibe? Do you like the really clear, almost English-like begin and end you see in Pascal? Or are you more of a fan of the short, sweet, to-the-point curly braces from C and Java? There's no right answer here. It's purely about the character, the personality you want your language to have. Okay, next up is writability. And this is pretty much the other side of the same coin. How easy is it for a coder to get an idea out of their brain and into your language? Makes sense, right? And usually, if a language is easy to read, it's also going to be easy to write. I mean, think about it. When you're coding, you're constantly reading what you just typed a second ago. This is such a classic example. I mean, count equals count plus 1. You can't get much clearer than that. But then C comes along with count plus plus. It does the exact same thing, but it's shorter, it's punchier, and for anyone who's been coding for a while, it's just as easy to read. So the question for you, the architect, is do you build in these kinds of power user shortcuts? Do you sacrifice a little bit of verbosity for writability? And last but definitely not least in this section, reliability. You want people to build stuff with your language that, works. You don't want it crashing all the time. A huge piece of this puzzle is something called type checking. It's basically the language's way of being a bouncer at a club, making sure you don't do something stupid like trying to add the number 10 to the word hello. It's a classic type error. And trust me, you want your language to catch that kind of mistake before the program runs, not when a user is trying to click a button. Okay, architect, you've made your first big call. Now for choice number 2. And this one's a philosophical battle. Do you give your programmers total, absolute freedom to do whatever they want? Or do you build in some guardrails, some fences to protect them from making catastrophic mistakes? This is the ultimate showdown, power versus safety. And this whole debate really comes down to one thing: memory. See, a language like C basically hands the programmer the keys to the entire computer. You get direct access to memory addresses using things called pointers. Now, this is awesome if you're writing, say, an operating system or game engine where every nanosecond counts. But you know the old saying, with great power comes a whole lot of ways to shoot yourself in the foot. And here's Exhibit A for the risks, the dreaded dangling pointer. Imagine a pointer is like a shortcut on your desktop pointing to a file. Now, what happens if you delete the file, but the shortcut is still there? You click it and chaos. Nothing happens, or your computer freaks out. That's a dangling pointer. It's a shortcut pointing to nothing, to a memory location that's been emptied out. And this leads to the kind of bugs, the soul-crushing bugs, that keep programmers up all night. So how does this actually happen? Let's walk through this C code. It's actually pretty simple. First, we grab a chunk of memory and make our first pointer, P1, point to it. Cool. Then we create a second pointer, P2, and make it point to the exact same place. Now we've got 2 shortcuts to the same file. Here's the killer move. We use P1 to delete that memory. But here's the problem. P2 doesn't get the memo. It has no clue the memory it was pointing to is now garbage. And boom, just like that, P2 is a dangling pointer, ready to cause havoc. So there it is, the dilemma in a nutshell. Pointers give you incredible, fine-grained control. But, as we're seeing, they are a one-way ticket to problems like dangling pointers and another nasty thing called memory leaks, or garbage. So, back to you, architect. You have to make the call. Is all that raw power really worth the danger?
Okay, architect, this is it. The final decision. You've figured out the look and feel of your language. You've decided how much you're going to protect your programmers. Now for the big one. How is the code actually going to run on a computer? This is all about the implementation method.
So you've basically got two classic paths you can go down. First, there's compilation. This is like translating an entire book from English to French before anyone reads it. You do all the work up front, and the result is a version the computer can understand directly. The payoff? It's crazy fast. The downside? That translated book only works for French speakers, just like compiled code only works on one type of computer architecture. Then there's pure interpretation. This is like having a human translator read the English book out loud, translating it sentence by sentence on the spot. It's way slower, we're talking 10 to 100 times slower, but the huge advantage is portability. As long as you have your translator, you can read that English book anywhere in the world.
But what if you don't want to pick a side? What if you want the best of both worlds? Well, that's where hybrid systems come in. This is the genius idea that Java really brought into the mainstream. You compile your code, but not all the way down to the metal, not to machine code. You compile it to this middle-of-the-road thing called bytecode. Then, a special program called a virtual machine, like the JVM for Java, runs that bytecode. The result? It's way faster than just interpreting, but you still get that awesome write-once, run-anywhere portability.
And it doesn't stop there. The tech got even smarter with something called just-in-time, or JIT, compilation. This is a really clever trick. Imagine our human translator from before, but this time they're smart. As they're translating, they notice you keep asking for the same chapter over and over, so they just pre-translate that whole chapter and hand you the finished pages. That's what a JIT compiler does. It finds the bits of your code that run all the time and compiles them into super fast machine code right on the fly. It's how you get the portability of the hybrid system with performance that starts to look a lot like a fully compiled language.
So, you did it. You made your choices. Maybe you picked readability over raw power, safety fences over total freedom, a hybrid implementation for that sweet spot of speed and portability. But here's the cool part, the big reveal. You didn't just design a language, you designed a way of thinking, a philosophy. Your choices, all added up, have created what we call a programming paradigm.
So, let's say you're the architect who went all in on control and speed. You wanted your language to be as close to the hardware as possible. Well, congratulations, you've built an imperative language. The whole idea here is that your code is a series of commands. Change this variable, loop through this array. Your variables are like little boxes in memory, and your code is just instructions for moving stuff between those boxes. It's the world of C, Pascal, and Fortran.
But what if you went the other way? What if you valued reliability above all else? You built in those safety fences to prevent messy, unpredictable changes. In that case, you've designed a functional language. Here, the whole game is different. You try not to change things. Instead of modifying variables, you just transform data by passing it through a pipeline of pure functions, kind of like a math equation. No side effects, no surprises. This is the elegant world of languages like Lisp and Haskell.
Or maybe you threw out the rulebook completely and took a totally different path. You might have built a logic language, and this is kind of mind-bending. With a language like Prolog, you don't write steps for the computer to follow. No, you just tell it a bunch of facts and rules about the world. Socrates is a man. All men are mortal. Then you ask it a question like, is Socrates mortal? And the computer uses logic to figure out the answer. You declare what's true, and it does the reasoning. It's a whole different universe of programming.
And that brings us right back to where we started. Why does Python feel so different from C? Because the people who designed them, the architects, stood right where you did and made completely different choices about these trade-offs. Once you understand that, everything clicks into place. You're not just a coder anymore. You're someone who gets the soul of the language. You know its strengths, its weaknesses, and exactly when to use it. And look, at the end of the day, this isn't just theory. It's about being a better engineer. Knowing this stuff helps you choose the right tool for the job. You can break out of that cycle of just using the one language you know best. Instead, you can look at a problem and say, you know what? This calls for a functional approach, or I need the raw speed of a compiled imperative language. That's a huge level up.
So your time as an architect is up. But I'll leave you with this thought. Now that you've walked a mile in their shoes, if you were going to design the next big thing, the next game-changing language, what would it be? What trade-offs would you make? Would it be easy? Would it be fast? Would it be safe? The future of programming isn't set in stone, and the choices the people like you make, well, they could end up defining how we all build that future.